All right, so I've started making videos and I've already done 11.4 and 11.5, and now I'm kind of working backwards. Now that I'm caught up, I'm going to start working backwards, and now I'm going to do section 11.3, which is the integral test. Okay. So since I'm kind of doing these out of order, I'm going to say some stuff that applies to 11.3 that I also said in the future. So if you're watching these in order, in future videos, you might hear some similar material. Feel free to skip over what's redundant. Okay. So I'm going to give a quick recap of what we've done so far. In 11.1, we did sequences, stuff that looks like this. In 11.2, we introduced series. So a sequence is an ordered list of numbers, and a series is we're adding up an infinite amount of terms. So in the sequence, this is just a list where we have AN. So we have a list, A1, A2, A3, and so on. And then in this series, we're adding all these up. It's something of the form. Okay, and these are very closely connected to talk. Both have convergence and divergence, right? In 11.1, we talked about the limit of this sequence, and if the limit exists, it's some finite number. We say the sequence converges. If there's no such number, we say the sequence diverges. And we can also talk about convergence and divergence of series. Okay, so how do we define convergence of series? We consider SK if instead of adding up an infinite amount of numbers, if we just add up the first K terms, we can do that. There's nothing weird about adding up a finite number of elements. We do that all the time. So if we add up the first K terms, that gives us a sum, and we call that sum the kth partial sum of our series, okay? So I can do that for every K. I can do that. I can add up the first one, just the first term by itself. That gives me S1. S2 would be A1 plus A2. S3 would be A1 plus A2 plus A3. So at each step, I'm considering a sum. And then on the left side, when I'm considering what that number, that total number is, this gives me a sequence, right? So this gives me a sequence, S1, S2, S3, and so on. And then if this sequence converges to a number using my techniques from 11.1, okay, let's say SK converges to C, then I say my series converges. And then I say the sum of my series is equal to C. Okay, so that's what I mean by convergence of series. Now for series, whenever I have a series, I first need to determine whether or not it converges. This is the question I ask myself about every series I see. So first question we ask, does it converge or diverge? If it converges, sometimes we'll try and find the sum, okay? So we could think of this as the second step of our series. And this is a big if. This, we can always ask ourselves this question, whether a series converges or diverges, but then even for convergent series, we can only find the sum in special cases when the series has a nice form. So in the last section, we saw we can find sums for geometric series, or telescoping series. Those are the main ones in our class. There are more, but there aren't too many more. And we can see just intuitively that it could get really hard to find sums of series. If I have a series an and these ans don't have a nice pattern, maybe I can tell it converges, but then how do I determine what the sum is if there's no underlying structure to this series? How can I figure out what adding up an infinite amount of terms, what number that's going to converge to? It's very difficult. So in 11.2, we saw some special cases of when we can do this, but oftentimes we can't. So that's why for a lot of series, we can only answer this first question. A lot of times we can't answer this second question. A lot of times we cannot find the sum. So most of our effort is going to be concentrated on determining whether a series converges or diverges. And you might be asking yourself, why do I need to know if I can't even figure out what the sum is? Why do I need to bother figuring out whether it converges or not? Well, it's very important for some theoretical aspects of math. Convergence or divergence, just the fact of whether a series converges or diverges or not, is hugely important. And that is often all the information we need. We often don't need the sum. So a lot of our tools that we develop are just going to be focusing on convergence of series. So we develop a lot of convergence tests. And there we saw in 11.2 that there's actually a divergence test as well. So remember the divergence test from 11.2. If I have my series from 1 to infinity of an, and the limit of an does not equal 0, meaning I look at the limit of the terms inside the series. If that limit doesn't go to 0, my series has to be divergent. Okay. And then there are several convergence tests, and maybe we could call the geometric series test. And when we have a geometric series of the form a times r to the n, we know the series is convergent for absolute value of r less than 1. Okay. And then if we have a telescoping series, we know the series is convergent if limit of an equals 0. Okay, so we could think of these as convergence tests as well, and we can find the sums in these cases. Okay. 11.3, we're moving into some slightly new material. We're going to see a convergence test called the integral test, which maybe is the first of a kind of new breed of convergence tests, in that we're going to test for the convergence of a series, and it's going to tell us whether or not our series converges. But it won't tell us anything about the sum. So we can't use it to find the sum. Okay, so as I said, a lot of the time we're going to be concerned with this first question: does the series converge or not? And we often don't even try and figure out the sum. Okay, so now we're moving into that phase of our study where we're going to use integral test to determine whether or not the series converges, and then we're going to ignore the question of the sum. Okay, just a little preview of how this works. Let's say I have my series an from 1 to infinity, and I can somehow connect these terms an to a function of x, f of x. Okay, so I'm going to take my series and I'm going to turn it into an integral. Okay, and how can I do this? An and f have to be related. How are they related? An has to be, f of n has to be an. Meaning, if I plug in 1 to f, then f of 1 should equal a of 1. And same thing goes for any other natural numbers. F of 2 should be equal to a of 2, and so on. And f of n should be equal to a of n. Okay, so that's how the series, my terms of the series, are going to be related to my function. Okay, and then once I have that, we can see that an and this f should be very closely related. And then I'm going to consider this improper integral. Remember, when we have infinity in one of the bounds, that's going to be a type 1 improper integral. So I'm integrating this function. This is a function, it's got a graph. Maybe I'm starting here at 1 and my function goes on forever. Okay, we can talk about this integral. Okay, if my function's positive, I can think of that integral as area, right? And I can take the integral to infinity by considering it as a limit. Remember our techniques from 7-8 about considering this integral. Okay, and improper integrals either converge or diverge, right? Just like series. And the convergence of this integral is very closely related to the convergence of this series. And it's just what you would hope. It's gonna, my integral is gonna be convergent if my series is convergent, and vice versa. If my integral is convergent, my series is gonna be convergent. And if my integral is divergent, my series is going to be divergent. Okay, so we already have the tools in our toolbox to tell whether this integral is convergent or divergent, right? So we're going to be given a series from 1 to infinity that meets some nice criteria, and we're going to turn it into an integral. And then we're going to use our previous tools to determine whether that integral converges or not. And then whatever we find out, the same is going to be true of our series. So we can see it's building on knowledge we already have, and it's going to be very useful. Okay, so let's explore the connection between the series and the function a little bit. And I find it very interesting, the connection between summation and integration. The fact is that this is actually a type of integral. And if you talk to some math people, depending on their background, they may or may not agree. But if you want to hear some fancy talk, we could say summation. This is of absolutely no use to you guys, but we could say summation is integration with respect to the counting measure. Like I said, that means nothing to you guys and it's of no use. I just felt like writing it. But whether or not you know what that means, there is a deep connection between summation and integration. And in fact, before we even look at this summation, recall how we developed the integral. Let's say I have a curve of a function and I'm trying to find, let's say that's my A and that's my B. I'm trying to find the area beneath the curve of my function. So how do I do this? I need to do the integral, right? The integral is going to give me the area between the curves, but how did I build my integral? I chopped my interval up into pieces, and I drew rectangles in each of those pieces. And then I added up the areas of these rectangles. So what is that width of that rectangle? Let's call that delta xk. And what's the height? We'll call that f of xk. And then my approximation to this area is going to be this. It's a sum. It's a finite sum. Okay. So I'm adding up the areas of these rectangles, right? I multiply f of xk, the height, times the width, f of xk times delta xk. That gives me the area of this rectangle. And then I add up all these rectangles and I get an approximation to the area. And these rectangles are all beneath my curve. So this is going to be a bit less, once I take my limit and take it to the integral, turn it into an integral, this approximation should be a bit less than the true value of my integral, right? On the other hand, if I had drawn my rectangles above, meaning I'd kind of overestimated my area, okay, then let's call this, well, we can represent it by, instead of xk's, let's call this delta xj, and let's call this height f of xj, okay? Then on the other hand, we should have the integral from a to b, f of x dx should be less than or equal to this, right? So we have these, let's kind of write out what we have then. Combine these two um, inequalities into one. Okay, so we have this. Okay, so we see that there's this nice inequality that really relates my integral to my summation. Okay, so how does this is just for forming my integral? How does this relate to my general sum, an? Now let's go to our series, our infinite series. Now this is going to help if we pick a specific series. So let's pick 1 over n squared. Okay. What is this series? Let's write out the terms for a little while anyway. This will be 1 over 1 plus 1 over 4 plus 1 over 9 plus 1 over 16. And then dot, dot, dot. Now I could multiply all of these by 1 and that wouldn't change anything, right? Okay. Now let's interpret each of these terms as the area of a rectangle. Okay. Let's see. 1 over 1 times 1. All right. So let's say the first part of each of these is the height, and let's say this 1 in each of these is the width of a rectangle. What does that area look like? Let's see. This would be a rectangle with height 1, width 1. Okay, so let's say I'm going to draw this here. Okay, let's look at this first rectangle. It's got height 1, width 1. Let's say it's starting here. Okay. So this first term would be the area of this rectangle, right? And what about this second term? Well, that would be the area of a rectangle with height 1/4, width 1. So something like this. All right. And then the next term would be a rectangle with height 1/9 and width 1, and so on. And then I'm adding all these rectangles together. On the other hand, think of my function 1 over x squared. Let's graph that. Okay. Let's see. It would be here, and it would on the left, it would be going up like this, and on the right, let's see. Oops. What have I done? Okay, let's try this again. I'm not drawing very well. Let's try and go to a new page. What I should have done is draw the graph first, the line first. All right, let's consider this graph, and it's obviously not to scale, but let's say this curve is my f of x, which is 1 over x squared, okay? And these rectangles are overestimation of my integral, right? If I wanted to find the integral from 1 to infinity, okay, imagine the rectangles keep going on, of f of x dx. I could approximate that with rectangles whose areas are in these shaded regions. And then let's start adding up these rectangles. Okay, what's the area of this one? It would be, let's see, we have 2, 3, 4, and so on. What is the area of this rectangle? Its width is 1, and what's its height? 1, which is 1 over 1. What about the next rectangle? Well, this rectangle it's got a height of 1 over 4 and a width of 1. And then next rectangle, it's got a height of 1 over 9 times 1. And if I added up all these rectangles, what would I get? I would get my series, 1 over n squared. I would have, why? Because it's 1 plus 1 over 2 squared plus 1 over 3 squared. That's the heights. Each of these is the heights. 1 squared, 1 over 2 squared, 1 over 3 squared, and so on. Okay. So I add up all these rectangles, and I get this approximation to my area under my curve, my integral. I get this, 1 over n squared. Okay, so I have one approximation to my integral. Let's kind of erase this stuff for now. And I'll rewrite this. So let me just rewrite neater what we have so far. I'm trying to approximate my integral, the area under my curve of 1 to infinity f of x dx. I can see that if I add up all these rectangles, it's going to be an overestimation. So I have my integral is less than or equal to Okay. And let's see, instead of having the general function here, I could write this. I'm talking about the specific function. One over x squared dx. And I see it's less than or equal to this thing. Now, how about, could I get a lower bound on my integral? Could I get a lower estimation? Yeah, sure. Let's look at these rectangles instead. Instead of going above the curve, let's stay below my curve. Let's look at these blue rectangles. I have a little technical difficulties here. There we go. How about these blue shaded regions? These are an underestimation of the area, right? And let's add up all these terms. Okay, so what are the areas of these rectangles? These blue rectangles. Well, let's see. This one, what's the height here at this right end point? That's 1/4. So the area of that rectangle is 1/4 times 1. What's the height of this rectangle? 1/9. So the area is 1/9 times 1. This one, 1/16 times 1. So what is this? What is the total of this area? That would be the sum from, let's see, n equals 2 to infinity of 1 over n squared, meaning it's my series, it's my same series, but instead of starting at 1, it's starting at 2, right? My first term would be 1/4. Okay, so I would start my series at 2. And I know this is smaller than my area. Okay, so let's summarize. Okay, I know my integral should be greater than or equal to this series. Okay, so what does all this mean? Let's see. If my integral converges, meaning if this value is less than infinity, then this value is less than infinity, right? And my convergence of a series is all determined by the tail. So if this piece, meaning this tail of my series, this is the tail of the series when I just ignore the first term, right? If this is less than infinity, then the whole thing has to be less than infinity. Okay. So I can see that if my integral is less than infinity, this series has to be less than infinity. And so my entire, my original series has to be less than infinity. On the other hand, if my original series is less than infinity, then the integral has to be less than infinity. And that's the motivation for the integral test. That's going to work not just for 1 over my series 1 over n squared and my function 1 over x squared. It's going to work for all series that have similar properties. Okay, so let's go to the actual statement of the integral test now. Okay, here's the statement of the integral test. Suppose f is a continuous positive decreasing function on the interval 1 to infinity, and an equals f of n. Okay, so what does all this mean? It just means, just like in this previous example, we have a positive continuous decreasing function f, and f of n, if I plug in n to f, I get a of n. Okay, so that's what the first part is saying. Okay. Then the series an is convergent if and only if the improper integral from 1 to infinity of f of x is convergent. All right, what does if and only f mean? It means these two conditions here. Basically, it means that the series converges if the integral converges, and the series diverges if the integral diverges. So that's what these two conditions here are saying. If the integral is convergent, then the series is convergent. If the integral is divergent, then the series is divergent. Okay, that's what we need to know for the integral test. So that is the statement of the integral test. And that's really the only thing we need for this section. We don't need to worry about estimating sum of a series. We can use the integral to estimate the sum of the series, but it's key that these values aren't necessarily going to be equal, okay? In a couple slides ago, we showed, okay, what was our inequality? We had n equals 2 of an is less than or equal to we had this, right? So this is an inequality. So even if I can figure out what this value is, that doesn't necessarily tell me what the sum of the series is. Okay, we don't know, we still don't know either of these. Don't know. And we don't know. So even if we can find the value of this integral, we don't know what this value is. We can use it to get a bound, but it might come up on the homework, but we're not going to need that for tests or anything like that. I'll go into this more maybe on the problem session for this section, but I wouldn't worry about estimating the sums of the series too much using this inequality. Instead of looking at that, let's look at how to test some series for convergence using the integral test. So let's consider this example here. We want to test whether this series converges or not. So since we're in section 11.3, let's try and use the integral test. So let's see, let's revisit the statement of the integral test and see what I need. All right, suppose we need a continuous positive decreasing function on the interval 1 to infinity such that a of n equals f of n. All right, well, how do I find that function? It's going to be pretty easy. We usually just replace n with x, and that's going to be our f of x. So I could replace n with x, and what do I get? I get 1 over x squared plus 1. Okay, that's a function of f, right? Okay, so let's use this, and what would be my first step? Okay, well, maybe first step is find the function, okay? let's actually pause here in the solving of our problem, and let's go ahead and write out some steps for this process in general. Okay, in general, if I am given a series an and I want to use the integral test, my steps would be, first of all, find f of x such that f of n equals a of n. And like I said, we're usually just going to replace n's with x's and call that our f of x. Step 2, we need to verify f meets all our criteria. What were our criteria? We needed continuous positive decreasing on 1 to infinity, okay? So we need to verify all that. And then let's see, what do we need? What else do we need? And then that's it. We're all right. We then integrate. Okay. Then we integrate f if integral f converges the series converges. If it diverges, the series diverges. So those are our steps. Okay. All right. So now let's try and apply that here to this. Okay. We found our, we could call this our step one. We found our f. All right. Step two, okay, is, we'll call this f. Is f continuous on 1 to infinity? Yeah, because we're never going to be dividing by 0, right? That's the only thing that could go wrong with this. F continuous. Boom. Boom. Is it always positive? Yeah. No matter what x I plug in, this is always going to be a positive number, right? So f is positive. Boom. Is f decreasing? How do I figure out if f is decreasing? Let's see, I could take the derivative. What's the derivative? Let's see. I could take the derivative, and if that derivative is always negative, then my function is always decreasing. All right. So let's see. This function is x squared plus 1 to the negative 1. I take the derivative. F prime would be negative 1 x squared plus 1 to the negative 2 times 2x. Okay, let's see. On the interval 1 to infinity, let's see, this would be positive, this would be positive, that would be negative. So when I multiply it all together, I get a negative number. So the derivative is negative on 1 to infinity. So my function's decreasing. If you were writing out a test, you would need to show these three, and for the decreasing, you would need to find the derivative to show the function's decreasing. That won't necessarily be required on the homework. So these three criteria will oftentimes, this step will oftentimes, be skipped. You'll just say, yeah, it's continuous. Yeah, it's positive. Yeah, it's decreasing. But for written tests, yeah, you would need to check that the derivative is negative, so the function's decreasing. A bit of a technicality there. All right, and then what would be the third step? The third step, let's see, what did we say the third step was? Integrate f. Okay, so let's see, I have my function 1 over x squared plus 1. The next step would be to integrate this improper integral. Okay, so I have this. I want to integrate this. Now use your knowledge from 7-8 to integrate this. How do I integrate this? Remember, this is an improper integral. First step, turn it into a limit. All right, and then I integrate for each t, all right? So now focus on this. What is the integral of this? Well, that's a tan inverse integral, all right? And then I evaluate from t to 1. Okay. So plug in the bounds would be the next step. Now I get this. So I'm evaluating this limit. Tan inverse of t as t goes to infinity. Well, let's see. First thing I could do is I could split up this limit into two limits. Okay. And this, let's see, this is a constant, right? Tan inverse of 1. Tan inverse of 1 is pi over 4. So the limit of that is pi over 4. So what I end up with is this limit minus pi over 4. Now, what's the limit of tan inverse of t as t goes to infinity? That is pi over 2. So my limit ends up being pi over 2 minus pi over 4 equals pi over 4. So my limit converges, okay, meaning this integral is convergent. My integral is convergent. Now, what does that say? What does the integral test say about my series? Let's see, my integral is convergent. That means my series is convergent. Okay. And that's what I wanted to know, right? I wanted to figure out if my series is convergent. So I figured out my original series is convergent. Now, what does the integral test not say? Okay, the integral test doesn't say the sum of my series is this, and in fact, it shouldn't be. The sum of my series should not be pi over 4. It could have some totally different sum. All it tells us is that if the integral converges, the series converges. So that's all the information about my series I can get from that test, but that's all I wanted. Let's try one more example. Let's try to determine whether this series converges or not. Using the integral test. Okay, so what's my first step? Finding an f. So let's just replace the n with x. I'll say f of x equals 2 over 5x minus 1. So that's my first step. Second step, I need to check all my criteria. Is my f positive? Remember, I'm focused on the interval 1 to infinity. Is it positive? Let's see, if I plug in a positive number here, let's see, even if I'm subtracting 1, let's see, I'm starting at 1, so I plug in 1 here, I get 5 minus 1, that's 4. And as x gets bigger, this is just going to get bigger. So that's always positive. This numerator is always positive, so my fraction should always be positive. Isn't continuous. Well, let's see. Again, I'm talking about the interval 1 to infinity. Am I ever going to be dividing by 0? No. It's always going to be continuous. And what about decreasing? Again, I would have to consider the derivative, okay, but let's see. If I consider the derivative, yeah, it's going to be decreasing. You could see that intuitively, meaning, okay, if I plug in bigger and bigger numbers for x here, I should get a smaller and smaller fraction. So my function should be decreasing. So all my criteria are met. Step 3, let's go ahead. I'll do step 3 over here. Now I need to integrate this from 1 to infinity. A little note about the bounds. My bounds of integration are going to be whatever the bounds are on my series. So if my series started at 2, I would start my integral at 2. It's usually going to be at 1, but just a little note there that the bounds are always going to be the same. So now I want to try and integrate this function. Okay, so now it's just a matter of integration using my toolbox of integration. Okay, again, I turn this into a limit. Okay, let's see. We could do a little u sub, or you could do a little mental math and see that. I'll let you guys try the integral on your own. It should be 2/5 ln absolute value of 5x minus 1. And we're evaluating from t to 1. Okay, so let's see. Let's come up here. When I plug in t, let's plug in our bounds. I get 2/5 ln 5t minus 1. When I plug in When I plug in 1, I get 2/5 ln of 4. What's this limit as t goes to infinity? Well, this is constant. And what happens to ln as t gets bigger? This is going to go up to infinity. So that's the limit is going to be infinity minus whatever that is, which is just a constant. So the limit is equal to infinity. Okay. So my integral diverges, right? It doesn't go to a finite value. Integral diverges. So the series diverges. All right. Again, I'll do a problem session video where I work several more examples, but that is the basic gist of integral test. Oh, one important, I should talk about one important consequence of the integral test. We can find a special case of the integral test when we're talking about series of the form 1 over n to the power p, okay? So I could either think of this as 1 over n to the power p, but that's the same as saying 1 over n to the power p. Same thing, okay? Let's, so n is the index, right? So I'm plugging in different n's at each step, right? And what's p? Let's say I'm gonna leave it general for now, but when you get a series, p is gonna be a specific number. So maybe p will be 2, or maybe it'll be 1.1 or something like that, but it's going to be, they're going to give us a number for p. But I want to find some conditions on p. So can I figure out ahead of time when this series is going to be convergent for different p's? I can by doing the integral test. Okay, let's say I had this series, just let's leave it general for now, and I wanted to do the integral test. I would replace n with x, and I would try and find this integral. All right, so the integral would look like this. I would set up as limit, then I would try and solve the integral. Let's see, if p, let's do two cases. Let's say p is greater than 1, okay? If p is greater than 1, then the integral would be, okay, the limit would be this, or the integral would, the antiderivative would be this. I would plug in bounds, and let's see, if p is greater than 1, this is still going to be 1. The answer will be 1 over x to the p minus 1. And this limit, let's see, when I plug in t, I'll get something like this. Okay, so if p is greater than 1, this limit's going to go to 0. This is going to be a finite number. So the integral will converge. Okay, so in other words, the integral is going to converge if p is greater than 1. On the other hand, if p is less than or equal to the 1, the integral is going to diverge. Okay, so convergent in this case, divergent in this case. So the integral test leads us to this really nice test we call the p-test. And that's for when we have a series of the form 1 over n to the power p. Okay, so the series is going to be convergent if p is greater than 1, divergent if p is less than or equal to 1. Okay, so that's a nice little consequence of the integral test. That is called the p-test, and we're going to use that a lot. All right, as I said, I'll upload a problem session video, but that's going to wrap it up for the little lecture.